Hey, Assalamualaikum. Very good afternoon, mate. Now, you might be wondering why am I sitting here reading a piece of paper that doesn't seem like there's anything. I'll answer that right away, right now. Before that, in chemistry, there is this term called isomers. In chemistry, isomers are defined as ions or molecules that have similar formulas but different distinct structures. Now, Frank Herbert once said, the beginning of knowledge is discovery of something that we don't understand. You see, did you ever wonder how did the term isomers come along? In 1828, a German chemist named Friedrich Wöhler made an interesting discovery, which was he found out that the composition of urea which is contained in our liver, and ammonium cyanide is quite an interesting compound, by the way. You guys can check it out. They actually have the same atomic composition, which is quite interesting considering the fact that back in those times they considered urea as something of very low standard and ammonium cyanide as one of the compounds to make a weapon, if I'm not mistaken. Okay, moving on. In that same year, Johannes Jacob Berzelius gave the term isomers to this weird phenomenon that they found out. Now, you might be wondering, where did they go after that? What happened after that? How did they continue to come up with different terms, etc., etc.? Well, in 1849, Louis Pasteur, I repeat, Louis Pasteur, a French biologist, by the way, remember, he was a biologist, and to think that he actually came up with a term that was going to be so crucial in chemistry is actually mind-blowing. Let's continue from that. How he found out was that when he was separating tiny crystals from tartaric acid, he found two mirror images. This actually became the fundamental to the discovery of optical isomers, which are actually isomers that can rotate plane polarized light in opposite directions. Okay, coming.
So the molecule that we were given today is 4,5-dihydroxy-2-hexene. So we were asked to construct the two-dimensional structure of the molecule. So from the hexene, we know that this molecule has 6 carbon. So we put 6 carbon in the structural molecule, and there are 2 in front of the hexene. So we know that there is a double bond at the second carbon, and after that there are 4,5-dihydroxy. So hydroxy is, we know hydroxy is a hydroxyl group. Dihydroxy means there are 2 hydroxyl groups, and 4,5-dihydroxyl indicates that the 2 hydroxyl groups is attached to the 4th and 5th carbon. Okay. Next, I will explain to you about how we want to construct a Fischer projection. First, Fischer projection is created to simplify the representation of molecules containing chiral carbon. So firstly, we need to indicate how many chiral carbons are there in the molecules, and the number of chiral carbons in the molecule indicates how many vertical lines can we insert into the Fischer projection. So as an example, from this molecule right here, I have constructed its Fischer projection. First, because it has 2 chiral molecules. Chiral molecules, so it has 2 vertical lines, and because it has 2 chiral carbon, it has 2 horizontal lines. So we draw 2 horizontal lines, and the vertical lines is the carbon chain of the molecule. Okay. One of the common mistakes that the student does when drawing a Fischer projection is they always forget to put the highly oxidized carbon at the top of the Fischer projection. Farhan, do you mind explaining about chiral carbon?
Yeah, sure. Okay, chirality. Chirality is a properties for geometrical isomers. Okay, how do we find chirality? Chirality is a compound that has chiral carbon. It has no plane of symmetry, and its mirror image is non-superimposable. Okay, so we go to the first rule. It has chiral carbon. Okay, what is chiral carbon? Chiral carbon is carbon that attach covalently to 4 different groups or atoms. Okay, for example, you look at this compound, chloromethane. Okay, this is the carbon, and the other 4 groups that attach covalently to the carbon, one is chlorine, the other 3 is hydrogen. So it has three same atoms and one different atoms. So it is not a chiral carbon. Okay, moving on to the next example. 1-propene. Okay, we take a look at this carbon. This carbon it has 1 hydrogen, 1 methyl, and it has double bond attached to CH2. So it has 3 groups that attach to it. So it is not a chiral carbon. Okay, next. Bromochlorofluoromethane. This is the carbon, and there are 4 different groups, which is chlorine, fluorine, hydrogen, and bromine. So we can conclude that it is a chiral carbon. Okay, next. 1-bromoethanol. Okay, we take a look at this carbon. This carbon, it has 4 different groups attached to it, which is bromine, hydroxy, hydrogen, and methyl. So it is a chiral carbon.
Farhan, do you mind showing me which are the chiral carbon in this molecule?
Okay, there are 6 carbon in this carbon change, but only 2 is the chiral carbon.
Why?
Okay, we take a look at this first carbon. It has 3 hydrogen and the other groups. So it has 3 same atoms. So it is not a chiral carbon. The second carbon is OH, H, CH3, and the other groups. So it has 4 different groups. So it is a chiral carbon. The third one is it has 4 different groups attached to it too, which is OH, H, C2, H4OH, and the other groups. So it has 4 different groups, and then it is a chiral carbon.
Oh, that explains a lot. Thank you.
Okay, well.
Plane of symmetry. What is plane of symmetry? Plane of symmetry is a plane that divides a molecule into 2 mirror image halves. And for example, we have a molecule of bromochloromethane, and as you can see right here, we have a vertical plane that divides this molecule into 2 mirror image halves. Alright. And must it be vertical plane only? No. It can be horizontal, it can be slant here or slant there. And for our molecule, which is 4,5-dihydroxy-2-hexene, Syazana? And as you can see right here, there is no plane of symmetry in this molecule, and thus makes it a chiral molecule. That's it.
So, I'll be talking about superimposable and non-superimposable. These are 2 terms that we will see very often if we're studying stereochemistry. So first of all, what is superimposable molecules? As you can see, it's identical when placed on top of each other. So for example, this chair. If you took another chair and placed it on top of it, it would be exactly the same, which is why you'd say that these chairs are superimposable. Non-superimposable molecules, however, they're not identical when you stack them on top of each other. So for example, your hands. If you place your left and your right hand on top of each other, they're not exactly the same, so you call them non-superimposable. In stereochemistry, our stereoisomers are all non-superimposable, which makes them all chiral molecules, as Farhan has explained earlier. So if they were superimposable, they would be achiral, and they would not have any stereoisomers.
Thank you, Razan. So, I will be explaining about enantiomers. As you can see here, enantiomers is a molecule that is non-superimposable mirror images. So this one is a mirror image for this. As you can see, it is non-superimposable. So next, I'm gonna show you about stereoisomers. It is a non-mirror images and a non-superimposable images. Syazana? For example, my molecule right here, compound 1 and compound 2 is enantiomers because it is a mirror image, but it is non-superimposable to each other. It is the same for compound 3 and compound 4, but compound 1 and compound 3, compound 1 and compound 4, it is distereoisomers. Same for compound 2 and compound 3 and compound 2 and compound 4. So, the next one is mesocompound. Mesocompound is an achiral compound, but it contains chiral carbon atom. For example, this is mesocompound. As you can see, it has carbon atoms, two chiral carbon atoms, but it has a plane of symmetry, so it is a chiral compound. So it is a mesocompound because it doesn't have any enantiomers or diastereoisomers. So this is the 3D molecule. 3D. This is 4 3D molecules of our molecule 4,5-dihydroxy 2-hexene. Razan will be explaining about the isomers.
So, as Alyaa has talked about enantiomers just now, we can see that compound 1 and compound 2, these two are enantiomers. Compound 3 and compound 4, these two are also enantiomers. And compound 1, 3 and 1, 4 and 2, 3 and 2, 4 are diastereomers. Okay. Now, today we've talked mainly about stereoisomers, which is only one branch of isomers. So isomers, there's also geometrical isomers, which we won't be covering today, but the 3 types of geometrical isomers are isomers in the form of chain isomers, functional group isomers, as well as positional isomers. So if you guys like, you guys can check about that too.